Okay, you can start, please.
Okay, thank you. Well, welcome back, everyone. So today's a bit different. The first 2 days you were in my lecture room. On campus today, I'm in my office. Still a strange experience. It's my 5th day or so back of the whole year. And yeah, so I'm going to use slides today and introduce really the subject of primordial black holes, so black holes from the Big Bang. And then I'll go back to the blackboard for the last 2 days. And so I want to be clear that although I'm going to present lots of results today, I'm not going to justify all of them. I'm not going to show mathematical derivations, and I'll come back to them for the next 2 days. It's a little bit experimental, but my hope is that by seeing sort of what the goals are and what the interesting things to do in primordial black holes are, and seeing their pictures, you'll feel inspired by what will look a little bit drier tomorrow when I'm, showing actual equations on the blackboard and deriving equations. Okay, so hopefully this will be effective. Now I'm going to start with asking you to join in. Okay, so I'm going to ask everyone, please really do join in. So if you go open a web browser, please, I've got 3 questions. Not going to spend forever on this, but I'd like to see how well you've understood. So if you go to polev.com/Byrnes, my name, okay, you should see that you're asked this question, and you should select the one correct answer. And I'm hoping it will work using this screen sharing setup, which I'm using now. I haven't used Poll Everywhere before in exactly the same setup. So can people see that? I'll give you a few minutes. The good news is it's going to use exactly the same web.
Could you please send the link in the chat?
Sure. So yeah, I think you don't need the www. Yeah, good idea. Okay. Okay, I see it's counting responses, so I see 8 people have voted. You can change your mind, and by the way, it's anonymous as well. That's what this mystery man is doing, or hat and sunglasses. So I'll give you another couple of minutes, and then a bit less time on the future ones when you're already logged on. We'll give 1 more minute. Hopefully everyone's on the website now. We've got 25 responses and 40 people logged on. So I'm hoping to get past 30 responses. Okay, we're up to 30. I'll stop there. I'm just putting the link back in because people who join late won't see the chat from before they joined. Okay, so hopefully, we're now down to 29. Do you want to revote? Okay, so we've got 5 options. Either all 4 are false, or one of these 4 is correct. Let's see what you thought. Okay, very good. Okay, 10% are being very optimistic. I'm afraid single field inflation does not generically create primordial black holes. generically, rather, the primordial power spectrum is far too small, and I'll show you in more details that today. Primordial tensor perturbations have been looked for at great depth, but they've not been found. What is correct is that, yes, as 72% said, the primordial perturbations, although they're close to scale invariant, they must be close to scale invariant. They cannot be exactly scale invariant. And this was the big detection, really, of the Planck satellite. The WMAP satellite already gave evidence in this direction, but Planck really made it completely clear. And they're not strongly scale dependent, and well, one of them was true. Okay, so that was that one. Then I've got same thing again. You should be able to say on exactly the same page, on your web browser, the same link, and once again, which, if any, of the top 4 statements is correct. And this time I'll give, I think, 2 minutes. Okay, up to 30 responses again. Last chance. If not, I'll close. So. All right, very good. So let's talk about each option. So about 1 e-fold of ultra-slow roll inflation. You need more than that. So you need about 2.3 e-folds of ultra-slow roll. Okay, the power spectrum was growing like e to the power of 6 times the number of ultra-slow roll e-folds. You need it to grow by about 6 orders of magnitude, 6 or 7 orders of magnitude. Then to produce eternal inflation, you need about 3.5 e-folds. So the first 2 are wrong, although they're not very wrong. Once again, the third statement is in fact correct. When the perturbations become of order unity, then that means the quantum mechanical fluctuations are so large that they're equally likely to push you backwards in the direction the inflaton is rolling down as they are forwards towards the end of inflation. So at that point, inflation, and at least in some parts of the universe, is going to last forever. And D is really wrong. The perturbations continue evolving outside of the horizon in ultra-slow roll inflation, which is completely different from slow roll. In slow roll inflation, they stop evolving at horizon crossing, or within 1 e-fold, say, of horizon crossing. Here, they just keep evolving. Okay, so there we go. Thanks everyone who participated. I was just going to quickly show the plot. So Pippa sent a link to this after the last, after the tutorial. So this is sometimes called the money plot, or the sort of the key plot of the Planck collaboration, at least with regards to their implications on inflation. So this is from the Planck paper. And you can see the dark blue as Planck, Weissop, and Keck data put together. The inner contour is 1 sigma, the outer contour are 2 sigma uncertainties. And the tensor to scalar ratio is less than about 0.0-ish, 6, 7, something like that. When you marginalize over the spectral index, it's less than about 0.044. Okay. And the exercise, the tutorial, was to calculate the predictions for m² phi² inflation. That's right up here. So the tensor to scalar ratio, depending on the number of e-folds, this is 60 or 50 e-folds. You see it's far too large. It's about 0.15. It's nearly a factor of 2 too large. And again, that was another big result from the Planck satellite, that what used to be a popular and very simple model of inflation has now been ruled out. And this is a figure I put in the notes. Okay, there are LaTeX notes. So, all right, we can see that the tensor to scalar ratio gives an upper bound on epsilon, given that our tensor to scalar ratio is 16 times epsilon. And that implies then that eta should be negative, at least when you include Weissop and Keck data, because then the spectral index, which we can see here, right, it's not consistent with being 1. So when it's not consistent with scale invariant perturbations, that would be this point on the far right. Well, then we need the eta slow roll parameter to be negative. Okay, and this is a sort of reconstruction I won't go into the details, but a sort of reconstruction of on a log-log scale of the amplitude of the power spectrum as a function of k. And because this spans a rather small range of scales on the y-axis, it looks like quite a strong scale dependence, but really this is rather mild. But nonetheless, you can clearly see this is tilted. This is not consistent with a flat scale invariant spectrum. The error bars become large on the left because of what's called cosmic variance, because there's basically very few observations you can make compared to the scale of the horizon. On the right-hand side, the error bars also become large because basically silk damping, the CMB spectrum becomes very hard to detect. And it's also a resolution effect. You're probing very, very small scales. Remember, K is the inverse of physical length. Okay, so that was just a brief summary from the first 2 lectures about inflation and ultra slow roll. I'm now going to move more onto primordial black holes, although there is a link, of course, to inflation. So one of the big questions cosmologists ask is, what is the universe made of? And we know that what we see by eye or with electromagnetic radiation is only a very small subset of everything that the universe is made of. Okay, so we see stars, we see planets, and with telescopes you see galaxies, but there's more, of course. And especially of interest is the dark matter. So I'm going to talk about primordial black holes, but first I have a question about astrophysical black holes, because we do know that stars can collapse. We know that when stars go supernova, for example, they can collapse and they can form a neutron star or a brown dwarf or a black hole. Okay, so if we think specifically about black holes, could the dark matter just be astrophysical black holes? And specifically for these 3 observations, which I believe Laura Covey spoke about briefly in her lectures. And it's the same link. I'll give 30 seconds more. We're nearly up to 30. Okay. Let's see how it went. Oh. Right, interesting. A very strong split. Very strong. So 41% said all of the above, 37% said none of the above. Let me be clear, I'm talking here about astrophysical black holes, not yet primordial black holes. So this time I'm not going to give the answer straight away. We'll talk a little bit more about the evidence, just briefly. Okay, so you've probably heard, I'm sure, of Fritz Zwicky looking at the peculiar velocities of, or the sort of kinetic energy of galaxies within galaxy clusters. It seemed to be too large to keep the galaxy cluster held together, hence there needed to be dark matter. Vera Rubin, especially famous for looking for galaxy rotation curves. And these are 2 of the classic pieces of evidence. Notice these are both made in the late universe, long after structure formation. Okay, so the evidence also includes the bullet cluster shown in this picture. Black holes are cold, they are dark. So based actually on late time observations alone, there's nothing wrong with astrophysical black holes. However, the growth of structure as seen from the cosmic microwave background, where the perturbations were of order, well, the power spectrum is awarded 2 × 10⁻⁹, meaning the individual perturbations are a few times 10⁻⁵. In order for those to grow quickly enough to form galaxies within a few billion years, requires a large reservoir of dark matter, which was not bound with not coupled, let's say, to the radiation, to the photons, and hence it could gravitationally collapse earlier than the gas in the universe, which was, especially the electrons, were coupled to the radiation until the time the CMB formed. So the reason why astrophysical black holes are not a good dark matter candidate is not based by itself on galaxy rotation curves or cluster velocities or even the bullet cluster. It's specifically from the fact that we need the dark matter to exist already at the time of the CMB, and then this is going well beyond my lectures, but constraints on the what's it called, the baryon to photon ratio eta, show that this is consistent, the constraints from Big Bang nucleosynthesis to the CMB. So we need the dark matter to exist before Big Bang nucleosynthesis, otherwise we'd see a change if the dark matter was formed out of baryons after Big Bang nucleosynthesis. So if I just quickly go back, the correct answer was all of the above, which 41% were correct. I'm just stressing that because in sort of research talks, when people talk about primordial black holes, they normally don't mention what's wrong with simply astrophysical black holes, which, after all, we know do exist. We don't know if primordial black holes do exist. Okay, so here's just the energy budget, and as you can see, we can only see with the naked eye a very small fraction of the energy, total energy components of the universe today. Now, how do we know? Well, I've talked about some. Let me just quickly show you a little bit of a clip from. The sound's a bit distracting, but this is a view of the stars rotating around the center of our galaxy. And it's based on real data, although it's been cleaned massively. Okay. So some of these stars are moving so quickly, they can be seen really making a complete rotation. Okay, now this is closer to real data. So you can see how the stars move around the center of our galaxy. Okay, and as you may probably know, this won the Nobel Prize for Physics last year, shared between 3 people, 2 for the sort of observational side, based on the supermassive black hole in the center of the galaxy, Roger Penrose, for theoretical work much earlier, proving that black holes really could form under realistic initial physical conditions. So black holes have been quite a hot topic for multiple reasons. One was that, another one was the Event Horizon Telescope doing what's called a direct image. Of course, it's not really a direct image of a black hole, but it's an image on the scale of the event horizon of the black hole, showing gas being swept and accelerated into the event horizon, or very close to the event horizon of the black hole. And of course, there's LIGO and Virgo detections as well, and I'm going to come to that and speak about that in more detail. Good. So the basic point is that dark matter, although it's normally assumed to be a new particle, and that's what, say, Laura Covey will have been focusing on, we don't actually know that. And the unique alternative, at least assuming general relativity to be the correct theory of gravity, are primordial black holes. Okay, now, as I've explained yesterday, we do need special initial conditions, and I'll come to that in more detail later. But we don't need new physics. We don't need beyond the standard model physics to form them. Okay, so if detected primordial black holes, they'd really teach us a huge amount about the initial conditions of the universe, as well as about the structure and the content, because then we would know what at least some of the dark matter is. And I give a link to a few review articles on primordial black holes. There's no textbooks, but there are good review articles. Okay, so what have we seen so far? Well, sorry, I should have updated this slide. We've seen sort of the light standard black holes, which were seen both for LIGO and Virgo through accretion of gas onto the black hole. Then supermassive black holes. I showed you two pieces of evidence: the Event Horizon Telescope with 1 million to 1 billion solar masses. The formation of these supermassive black holes is really very uncertain. And then, well, it's actually now gone much beyond this, up to about 60 or so solar masses detected by LIGO and Virgo. Now, a particular interesting thing to look for would be those which are too light to form astrophysically. So those below the Chandrasekhar mass, or more specifically above the Tolman-Oppenheimer-Volkov neutron star limit, which is about 3 solar masses. Okay, so we believe in astrophysics, anything lighter than about 3 solar masses cannot be a black hole. It could be a neutron star, and anything lighter than about 1 solar mass simply shouldn't exist. And this is an old plot. I'll show an updated one later, but of sort of the known neutron stars. This is about 2 years ago. The LIGO-Virgo detection plus a few of the known black holes from X-ray, well, in X-ray binary pairs, and then the LIGO-Virgo first ones, which you see tend to be rather more massive than the ones observed by other means. Yeah. This may also be a selection effect, because the more massive ones are easier to detect via gravitational waves. But when that detection was made, of course, everyone was thinking about, well, what do we do with the LIGO-Virgo gravitational wave detection? And this paper caused a bit of a stir, which was, did LIGO detect dark matter? Suggesting that perhaps all or most of the dark matter was in the form of black holes, primordial black holes, which are significantly heavier than a solar mass. And people have been debating this ever since, although there is now more or less a consensus that it cannot be the majority of the dark matter. In fact, it appears unlikely that more than about 1% of the dark matter could be out of LIGO mass. By LIGO mass, I mean between about 10 and 50-ish solar masses. However, arguably, all of the LIGO black holes could be primordial, or at least that was true just based on the merger rate, just based on how many it would need, and based on other constraints on primordial black holes. Well, of course, we'd like to find out, but we have a challenge, which is once black holes are formed, they have no more hair, so-called the no-hair theorem, which basically means they have very, very few properties. Okay, a black hole has mass, it can have spin, and then when you've got a binary pair, you can also look at the mass ratio. You can look for the redshift distribution and location, but once a black hole is a black hole, there's really very little memory left of how it formed or when it formed. So this is, of course, challenging. Okay, so here's a picture of LIGO, these 4-kilometer long arms. This was the 2017 Nobel Prize. The black holes have been on a winning streak. As I said, what happens in a black hole stays in a black hole. So how did it form? Well, we have to deduce it indirectly. I'm going to skip towards the end of this, but this is what LIGO-Virgo, so I was hoping. Here we go. Okay. So it saw towards the end when once the two black holes are not much further apart than their own Schwarzschild radii, or Kerr in the case of rotating black holes. So it's only when they're very close that they're moving close to relativistic speeds, and that's when the gravitational wave signal becomes loud enough, although it's still very, very weak. This is massively slowed down. Okay. There's the merger, and then almost instantaneously it forms a new black hole, which is perfectly spherical. So the ring down lasts just a tiny fraction of a second. And then you're left with a new black hole with a larger mass, but with no history anymore that would be visible in the new black hole or about where it came from. So that was the three major phases: in spiral, merger, and then the ring down. And so far we don't see the ring down. So, well, I was saying, how could we know? Well, I won't go into details, but one potential piece of evidence for a primordial origin is the fact that the vast majority of the black hole mergers detected are consistent with there being zero spin of the black holes. They don't directly measure the individual spin, sadly that's too difficult, but what they measure is a sort of mass-weighted sum of the pair of the spins of the two black holes put together. And so this chi-effective parameter can be between -1 and +1. And for the vast majority of the events, not all, but the vast majority, it's consistent with zero spin, which itself is then consistent with both black holes not spinning at all. It's also consistent with other alternatives where the net spin adds up to zero, but the simplest, perhaps, explanation would be that the black holes are not spinning. Now, if you think of an object as big as the sun, with a radius of something like 1 million kilometers, it needs to shrink till its radius would be 3 kilometers to form a Schwarzschild black hole. Okay, so given that it's spinning, you would naively at least expect, as it shrinks, because of conservation of angular momentum, the angular velocity should spin up dramatically and hence lead to something rotating very, very quickly. And that is seen with some X-ray observations. It's seen with a few of the LIGO-Virgo events, but it's not seen with the vast majority, which rather are consistent with no spin. Okay, so that may be a hint for a primordial origin. However, there are also ways where the final collapse into the core can sort of eject the angular momentum. Honestly, I've never worked on this, the astrophysical formation mechanisms, but I'm just saying that it's far from definitive. So this is something I looked at with some collaborators, Alex Hall and Andrew Gell, who's my nearly finished PhD student. We did the first Bayesian model comparison between either purely astrophysical or purely primordial black holes. So a model comparison means that you're really asking for the relative goodness of fit between these two models. Okay. I won't go into the details. This goes through Bayes' theorem. But what you need then are to be able to calculate the merger rates for primordial black holes by assuming some functional form of the masses. We had some discussion before about whether they would be monochromatic. The answer is realistically no. They'll have some range of masses, so we assume a lognormal mass function. We fit a peak mass somewhere in the middle of the LIGO-Virgo data. We fit a width and we fit an amplitude. We take broad priors. We also compare with an astrophysical model from the LIGO-Virgo papers, which are really just parameterizations of the merger rate, with some input from astrophysics, but not very much. It's more a parameterization. And we asked then, well, how well does the data fit, say, purely primordial origin versus a purely astrophysical origin? So one of the key parameters are what is the width of the primordial mass function. The wider the primordial mass function is, the wider the range of masses you will see with LIGO-Virgo. Okay, if it's close to monochromatic, then you'll basically always keep seeing the same mass. You'll also keep saying the same mass ratio, which will be 1, because if all black holes have the same mass, clearly every merger would be, in a sense, boring. It would always be the same two equal masses colliding. Now, as you make sigma wider, which corresponds to the width of the mass distribution, it's going to become more and more likely that you see very unequal mass mergers, one from the top end, the heavy mass side, and one from the light end. So we can look at how the distributions look for the total mass and for the mass ratio of these primordial black holes and compare it to, again, just one parameterization of the astrophysical. I'm completely oversimplifying the astrophysical. There's not like one model, there's not one prediction, but to make the model comparison, we have to choose one. And clearly, again, a monochromatic mass function is ruled out already because LIGO-Virgo have seen a broad range of masses. So in a bit more detail, again, here's sort of the predicted merger rate, the number per year, both for the LIGO-Virgo models in terms of the total mass. They don't look so different, but they look a bit different. In terms of the mass ratio, primordial black hole models, which are at least a good fit for the data, are much more likely to see an unequal mass ratio than astrophysical models. There is an astrophysical reason, because if the binary existed as a star before they both went supernova and individually formed black holes, then you can have some sharing of the gas, which can equilibrate the masses. In terms of redshift, you might think, well, obviously primordial black holes exist at much higher redshifts. They existed long before stars. So you would expect to see them merging at high redshift. And in principle, with good enough instruments, that is true. And with something like the Einstein telescope, which is proposed to be built in the Netherlands, they really would be able to probe up to high redshifts, redshifts greater than 10, perhaps. And at that point, you wouldn't expect to see astrophysical black holes merging. But for the moment, with the real sensitivity of LIGO and Virgo, you don't expect to see that. You're going to see basically the same redshift distribution. Okay, so now by eye, you might think, well, this is the key, the mass ratio. But actually, if you look at the constraining power of the LIGO-Virgo instruments, most of their constraining power goes on either the total mass or the chirp mass of the merger. So we fit a log-normal mass function, we compare the best fit. So FPBH is the fraction of black holes in dark matter. The best fit value is very small. It's much, much less than 1. It's about 3 times 10 to the minus 3. If most of the dark matter in primordial black holes were these sorts of masses, then we would see far too many mergers. They've had a long time to form binary pairs and to come close to each other. So you would expect to see far too many mergers compared to the actual merger rate. So once again, we're doing a very simplified thing. In some ways, it was still very complicated, but we are comparing either only mergers from astrophysical black holes versus only mergers from stellar black holes. And we find that primordial black holes are really strongly disfavored as an explanation for all of the events, both in terms of the Occam factor, which asked you about sort of what fraction of your prior volume, of your prior parameter space would be a reasonable fit to the data, and also in terms of the best fit value, they're disfavored. Okay, so this was just using 0102 data, and already that data was inconsistent with having seen only primordial black holes. That doesn't say anything about there being a mixed scenario with both, but it really disfavors only primordial black holes. That was assuming a log-normal mass distribution. We did think about, well, that's a reasonable prediction. It's by far not a guaranteed prediction. So we thought about using some more complicated models putting in some cuts, putting even a bimodal mass function, nothing really helped. So this is just showing the chirp masses, okay, M chirp of the detected events. You can see there were two sort of lighter ones, plus a majority of heavier ones. Now, with a log normal, the problem is a log normal tends to have a long tail to heavier masses. So the primordial black hole one, in order to fit the heavy ones, it would tend to expect more even heavier ones. Alternatively, if you shift the peak of your mass distribution too far to the right, then you don't get enough, you don't get the two light ones. Whereas astrophysical black hole models, because they've expected to see some sort of mass gap, both to light and to the upper end, it's easier for that astrophysical model to fit both at the same time, both the lighter and the heavier end. Okay, I'm not going to go into all the details, you know, this is really at the level of a conference talk, but I'm just trying to sort of sketch what the main implications of the results were. So yeah, we tried different mass functions, we tried going more complicated, we tried a skew log normal, we tried even bimodal peaks. We basically thought, well, given that we don't know the underlying model of inflation, let's fine-tune as much as we like, just to see if we can find a good fit, and the answer was we couldn't. We also haven't thought about or included accretion onto the black holes, which for a primordial black hole, it's got, you know, 14 billion years nearly to accrete. Accretion, though, occurs most strongly on the heaviest mass end. So the heaviest ones are going to be even heavier following accretion. That's going to make your mass function broader, and in particular, overproduce the very heavy ones, which LIGO-Virgo is perfectly capable of seeing, but hasn't seen. Well, that's not quite true with O3 data, with O3A. It's all one, but with primordial black holes, you'd expect rather much more than one event at the upper mass end. So there's a reasonable consensus, I believe, in the community. Several people have checked our results and go and also redone it with O3A LIGO-Virgo data. They're either exclusively or primarily seeing astrophysical black holes. The properties of these black holes are somewhat unexpected, but modeling stellar collapse is hard. So maybe we shouldn't be too surprised that, you know, that the models were not quite right. A mixed model is still perfectly possible. But the best thing we can hope for is a sub-Chandrasekhar mass compact object, because that really shouldn't form astrophysically, and so that would be a clean probe of a primordial black hole. So here again is an updated plot now. You can see there was a question in the office hour about the heavier ones. Well, here you see one with about 60 and 80, 90 solar masses. This is towards the upper end. It's not where you'd really expect to form them astrophysically, but of course they could be second generation, meaning they could have formed from what was already a merger beforehand. There's also some tentative evidence for things in the lower mass gap, something between about 2 and 4 or so solar masses. Again, tentative, it could be a merger of, again, second generation from a merger of neutron stars. The best would be, you know, to go just a little bit lower, because again, the Chandrasekhar mass, it's not very precise exactly what the lower band should be. But the good news is LIGO-Virgo are capable of seeing things even lighter, significantly lighter than 1 solar mass. So there have been searches for even much, much lighter, right down to 0.1 solar mass mergers. They're very numerically hard to do. They involve many, many in-spiral rotations. They last, the signal is long, but very, very weak because of the low masses involved. They haven't got a detection. They found a constraint on the fraction of primordial black holes in dark matter. Okay, it's a very indirect constraint, but it's through not overproducing a merger rate such in order to explain the fact they haven't seen any mergers. And this right-hand figure shows the maximum distance at which an equal mass merger of subsolar mass black holes could potentially be seen. So, in principle, 2 10 to the minus 4 solar mass black holes, and that's, sorry, 10 to the minus 4 solar mass black holes, which is vastly below the Chandrasekhar limit. Could be seen, provided they were closer to us than the Large Magellanic Clouds. And if they're inside the Milky Way, it could be closer to 10 to the minus 5. However, again, the fact that it could be seen doesn't mean that LIGO-Virgo would have seen it, because they would have need to have searched for that template. And it's a numerically very expensive problem. They would have to search for every possible template, every possible sky orientation, position, etc. And also, there's no reason why they should be equal mass, mergers, etc. So it's a difficult thing to do, but that's what, primordial black hole aficionados will be hoping for. Okay, so I've got a quote from a popular science article in Quantum magazine, which is, advocates of the primordial black hole hypothesis still have a lot of convincing to do. Most physicists still believe that dark matter is made out of some kind of elementary particle, one that's devilishly hard to detect. Moreover, the LIGO black holes aren't too different from what we would expect if they came from ordinary stars. It sort of fills a hole in the theory that isn't actually there, said Carl Rodriguez. There are things that are weird about some of the LIGO sources, but we can explain everything we've seen so far through normal stellar evolutionary processes. Now, not everyone would agree with that final quote, but it's clear at least that, there's freedom to potentially explain it all without primordial black holes, and there doesn't appear to be freedom to explain all of them only through primordial black holes. I think I'm going to change direction quite a bit, so I think I'll ask if there are any questions now before I continue.
I have one question. So in page 34,
Yeah.
so in the leftmost panel, when you calculate the merger rate, because I imagine that depends on the number of binaries, on the primordial black hole binaries, what is the assumption on the formation of these pairs?
Right, very good question. Yeah, I've skipped over all of that. So the assumption here is that they form binary pairs in the very, very early universe when they form, well, not when they form, but quite shortly after they form, when they're very close to each other, simply because the universe was much smaller. And that these binary pairs then, after they've formed, they've got very elliptical orbits and they basically in-spiral for the vast majority of the age of the universe. And there is a caveat there, which is that we're assuming that the binary pair is not disrupted by an interaction with a third object. And people like Karsten Jadamzik have done numerical simulations. They have found that if the fraction of primordial black holes in dark matter is large, much larger than the values we consider, then the merger is important. Sorry, the disruption is likely to be important. But for the sorts of values we're looking at, the best fit values we find of about 3 times 10 to the minus 3 fraction of the dark matter being in sort of these sorts of masses of primordial black holes, disruption is quite small.
Thanks a lot.
Okay, you're welcome.
I have a question. I was wondering if there is a reason to compare the model, to make the comparison between only astrophysical black holes and only primordial black holes instead of the only astrophysical black holes and the mixed model.
Very good question, and honestly, not really. We did it, because, well, it was the first thing to do, and it's significantly more difficult to do the mixed. But after we did this, other groups, one with Antonio Riotto and a group in Geneva, looked at a mixed model. And they found a mild preference actually for a mixed model, but with only about, if I remember right, about 1/5 of the mergers being due to primordial.
Okay.
So yeah.
Okay, thank you.
Yeah, I'm just presenting the work I know best, which is what I did. Well, I didn't, other people did most of it, but I was involved in it. Yeah.
Okay, thanks.
You're welcome. Okay, anyone else?
May I ask a question?
Mm-hmm.
So, is there some motivation for this log normal mass distribution?
There is. It's not compulsory, but we'll talk a little bit about that in the next 2 days. It's to do with this phenomena called critical collapse, which I'm afraid I haven't got slides about, but basically, even if your primordial power spectrum is very narrowly peaked, let's even assume it's monochromatic, so it's like a delta function, which in itself is not realistic, but assume it was, then density perturbations larger than a certain value, called the collapse threshold, will form a black hole. However, the mass of the black hole, although it's roughly equal to the horizon mass, and for my lectures that will be a good enough approximation, in reality the actual mass will depend on how much the density contrast, the density perturbation, is larger than the collapse threshold to form a black hole at all. So if it's much larger, you form a heavier black hole. If it's only a tiny bit heavier, you form quite a light black hole. And that phenomena tends to give you a log-normal sort of distribution with a sort of tail to heavy and light end and a reasonably narrow peak, but nonetheless not, not monochromatic.
Okay, thank you.
Okay. Anyone else? If not, maybe it's a good moment to take a coffee break. I see it's 50.
Okay, then I will stop. I will pause the recording. Okay.
Yeah, please. So if we, yeah, very good, thank you. Okay, so now I'll talk a little bit about how primordial black holes might form. Again, more details will follow with equations on the blackboard. But let me just give you a sketch. So the mechanism I'm going to assume is that they form from large amplitude density perturbations shortly after the time of horizon re-entry. Okay, when the modes are outside the horizon, they're causally disconnected. Basically, the length scale of the perturbation is too large compared to the scale of causality. But after re-entry, if your density perturbation is very large, you can have a fairly rapid collapse in about 1 Hubble time to form a primordial black hole. And because the horizon scale always has a corresponding horizon mass, also corresponding time of horizon entry, there's a one-to-one relation between horizon entry, horizon length, horizon mass, and that gives you an order of magnitude estimate for the primordial black hole mass as well. So what is this collapse threshold? This has come from numerical simulations by Musco-Miller. I'll sketch the idea behind an analytic estimate, but from numerical simulations, well, the answers depends on the background equation of state. The case we're interested in is radiation, which is what, a third around here, where delta critical is about 0.45. Okay, so if the density contrast measured at horizon entry is larger than about 0.45, then you collapse and form a black hole, and that will form quite quickly. If you're smaller than the huge radiation pressure, we're thinking in radiation domination, and the early universe is so large that it just blows everything apart, and you don't form a black hole. If the equation of state is reduced, then it's easier to form a black hole because there's less background pressure. Okay, but you can't trust this in a limit of zero, of zero pressure, because this assumes spherical symmetry and various things which will break down in the limit of a small value of delta critical. Okay. There is a little bit of a link, don't worry about all the details, but there's a little bit of a link between the shape of the primordial power spectrum and the density profile. Okay, again, assuming a spherically symmetric density profile, you can get a little bit different density profile, and that leads to a slightly different value of delta critical. That was shown on this plot with different values of alpha parameterized different profiles. But you see, the answers don't change very much. Delta critical is not very sensitive to the density profile. So for the purpose, of this introductory lecture course, we'll ignore that dependence. However, we will think about changes to the equation of state. And And the reason why that's important is that it's related to this Chandrasekhar mass, just by coincidence. So there's a nice cosmological coincidence, which is the time of the QCD transition, when the quarks bind into hadrons. It's about a microsecond after the Big Bang, when the temperature is about 200 MeV. And the key thing is that the horizon mass at this point is 1 solar mass, to very good accuracy. Okay. And this really is a coincidence, because the horizon mass from the end of inflation until today has changed by about 50 orders of magnitude. And yet there's an important physical scale when the horizon mass happens to be 1 solar mass. So what happens? Well, when the horizon mass, basically the pressure evolves as the QCD transition takes place, and because you've got a transition, not really a phase transition, but a mild transition, the pressure reduces. So the pressure reduces, and the peak reduction in pressure occurs about, again, the blue line is the equation of state, when the equation of state is about 1 solar mass. Now this is going to lead to additional primordial black holes forming, because the pressure is lower, so it's easier to form them. And just briefly, well, there's been various sorts of transitions within standard model physics as a function of the energy. So at very high energies, 10 to the 5 MeV, you've got the electroweak. Then you have the QCD at about 100 MeV, and then much, much later, the electron-positron annihilation around the time of Big Bang nucleosynthesis. Okay, every time there's this sort of transition, there's a reduction in the equation of state, the pressure, but by far the most important is the QCD one, which is a lovely coincidence, because the mass, the horizon mass at this time is very interesting. So what happens? Well, you get some mass function of primordial black holes. Okay, so this is the fraction of dark matter in primordial black holes, assuming a particular amplitude of the initial perturbations, which notice is very large. It's much, much larger than the amplitude observed on CMB scales, which is more like 10 to the minus 9. Okay, so it needs to be much, much larger. We still need this period of ultra slow roll or something like that. Without it, you won't get any, with just standard slow roll inflation, you won't get anywhere near this amplitude, and you won't get any primordial black holes. But the point is, if you did have primordial black hole formation by having a large enough amplitude, then you get a huge boost by about 3 orders of magnitude on the solar mass scale. And why it's so many orders of magnitude is to do with this exponential dependence, which I'll explain briefly on the blackboard on tomorrow. But the mass function is exponentially sensitive to the collapse threshold. So when the collapse threshold is reduced, because the equation of state is reduced, you form exponentially more. And so that's a very nice fact, and it's just a nice coincidence. Now, that was assuming exactly scale invariant perturbations, and remember that cannot continue too far, because that's completely ruled out on the observable cosmic microwave background scales. So if you add in some spectral index, assuming it's constant for no good reason, just for simplicity, you see how the shape, now the mass function can change shape a lot, but nonetheless, compared to the dashed line, which was...
Buongiorno. Buongiorno a tutti.
Oh. Somebody needs to mute their microphone, I think. Right, there's this 3 orders of magnitude enhancement.
Condivido lo schermo, così magari mi date conferma anche del fatto che si vede.
Okay,
Perché stai condividendo lo schermo? Sorry, just a moment.
Okay.
Yeah, I think it was was thinking about another meeting. Okay, please go on.
Okay, no problem. Okay. So yeah, that was the basic idea, right? The reduction in pressure will lead to an enhancement of primordial black holes if they're forming on that sort of scale at all. Of course, they might not be. Now we'll talk a little bit about observational constraints. This will come up again more detail on Friday. So here's a plot, and it's very important. So FPBH is the fraction of dark matter in primordial black holes today. Okay, so 1 means all of the dark matter in primordial black holes. 10 to the minus 2 means 1% of the dark matter are in primordial black holes. And there are various constraints. There's constraints from gravitational wave, from the merger of primordial black holes. I've briefly mentioned this with regards to LIGO and Virgo. You can see this has the tightest constraint at around 10 to the 2 solar masses, because that's where they're most sensitive, and no black holes where the primordial astrophysical have been seen with 100 solar masses. Then there are microlensing constraints, which basically means you stare at a patch of the sky, for example, a Large Magellanic Cloud or Andromeda Galaxy, and you look for random lensing signals of black holes or other compact objects passing between the telescope and the background stars. And that should cause a brightening of the light if you get some lensing around them. And there's a few tentative detections, but nowhere near enough to explain all of the dark matter being in primordial black holes. And the detections which there are might be, of course, something else, some other compact object. It doesn't prove, it's not like a gravitational wave detection, where it really has to be so compact that it has to be close or a black hole. It could be, for example, a loose planet, which is somehow floated out of a galaxy. But there is a window, and a fairly uncontroversial window, where you're allowed FPBH equals 1, so all the dark matter in primordial black holes, which is around an asteroid mass. So in terms of grams, about 10 to the 17 up to 10 to the 21 grams, or in terms of solar masses, around 10 to the minus 16 or 10 to the minus 12 solar masses. Okay, so in this window, you're fine. Elsewhere, you can have instead a mixed dark matter window, where you have a subdominant fraction of primordial black holes, around 10% or 1% or 0.1%, plus the rest of the dark matter then needs to be something else. Okay, so this is the least sort of controversial window. The constraints come from different redshifts. I won't go into details. I just thought this is a very nice plot from this review article by Carr and Kernel, showing you know, the microlensing constraints come effectively from redshift 0. Then there are some constraints, for example, from supernova, from studying galaxies at redshift 10. Then at redshift 1000, there's constraints from the cosmic microwave background. So, you know, if there's accretion or mergers, you have to be careful when you think of a mass function, especially if you see monochromatic. There will be some evolution with redshift, and then the constraints also come from different redshifts. So, you know, these plots can never show you all of the information, because that plot is made today, but it's not taking into account the potential change in mass as you go through time. Nonetheless, I think the fact that you can't have all the dark matter in primordial black holes of anywhere close to a solar mass or beyond is a pretty robust conclusion, even if you also think about broader mass functions. Okay. Now, the constraints in this asteroid mass window have changed again and again and again. People like to try and rule it out. For example, from femtolensing of quasars. There's been microlensing, which people have thought extended, but then have been shown wasn't correct. There's a potential constraint from the destruction of white dwarfs. If you have white dwarf stars, they might capture very light primordial black holes, which then eat up the white dwarf. Once again, this appears not to be a robust constraint. But if you look for these sorts of constraint plots, you can find literally hundreds, if not thousands, in the literature. And they'll all show you somewhat different constraints. Some will show you no dark matter window, but to the best of my knowledge, any attempt to rule out this window has been proved wrong. Or at least, let's say, not rigorous at all. And there was a very recent case that Siraj and Avilov, who's quite well known for his aliens idea, this was submitted on the 8th of March with this very strong title, Eliminating the Remaining Window for Primordial Black Holes as Dark Matter, using the idea that the Kuiper belt, which is somewhere outside the radius of Saturn, of very small asteroids would have been disrupted by primordial black holes. But 6 days later, on the 14th of March, they withdrew the paper saying the constraints weakened significantly. So just a warning, you know, sometimes even, this one wasn't even published, of course, not in 6 days, but other results have been published, but nonetheless haven't stood up to longer term scrutiny. Now, okay, but anyway, so we've got lots and lots of constraints of FPBH, the fraction of dark matter allowed today. What about the constraint on the allowed fraction of dark matter to collapse into black holes at the time of formation? That fraction is normally called beta. And this fraction is much, much smaller than the sorts of constraints we're talking about on FPBH today. I'm not for a second going to try and tell you what all of these different constraints come from, but you should notice one thing: the constraints get systematically tighter and tighter as you go towards lighter masses. And there's a very simple reason for that, which is the same as for any sort of dark matter formation mechanism. You only need to form a very small fraction of the background universe in dark matter if you form it early, because after the time of formation, the dark matter will decrease or dilute like a to the minus 3. The background is radiation dominated. Remember, radiation scales like a to the minus 4. So the background will decrease, and the total energy density will decrease like a to the minus 4 until the time of matter radiation equality, whilst the primordial black holes will decrease like a to the minus 3. So in the end, their relative importance is boosted by a factor of a from the time of formation until the time of matter radiation equality. Okay, so by this factor. And this factor can be very, very large. It can be many orders of magnitude, and that's why you see this tightening of constraints. Eventually, the constraints stop getting tighter, and that's because we're then looking at such light black holes that these would have evaporated by Hawking radiation before or around the time of Big Bang nucleosynthesis. And it's getting very difficult to probe what's happening to a subdominant fraction of the universe 1 second or 1 minute after the Big Bang. Okay, but again, I'll show this, you know, I'll derive this more carefully on the board, but hopefully it's clear that if you want to form all of dark matter and primordial black holes at a late time, then yeah, there's not much more dilution of the background until matter radiation equality. If you form them early, they form earlier because that horizon scale re-entered the horizon earlier. That length scale re-entered the horizon earlier, and hence you need a much, much smaller fraction to form even all of the dark matter today. Okay, so maybe I'll ask if there's any questions about that before I start talking about the initial conditions and link this a little bit to inflation.
Sorry?
Mm-hmm.
So you said that even if the equation of a state decreases during the QCD phase transition, we still need some non-standard, slow roll inflation scenario to produce PBH. Is that correct?
Absolutely, yes. Yeah, the equation of state doesn't drop to 0. It doesn't drop so dramatically. So you still need a large enhancement of the power spectrum, yes.
So this distribution that you showed later in the next slide, I think this would be on top on the enhanced power spectrum.
That's right. Yes.
Okay. Okay.
Yeah, I want to be clear about that. This doesn't happen naturally. You still need to boost the amplitude a lot. But if you do boost the amplitude a lot, then the point is you will get many more solar mass objects than you would have expected, because the equation of state is not a third, it's a bit less.
I see.
But
I see.
you still need that boost, yes.
Okay, thank you.
Is there anything else? If not, as I say, I'll come back to these things on the blackboard. But now I'll talk a bit about the initial conditions. So, right, we see on the very large scales, the cosmic microwave background, large scale structure, that the amplitude of the perturbations, and we see that they're close to scale invariant. As you did in the exercise, we can calculate the spectral index. It's very close to unity, so close to scale invariant. Now, this probes about 2 decades or so of length scales, 2 to 3 orders of magnitude in length scales, which corresponds to about 5 to 10 e-folds of inflation. But as I've told you on Monday, we expect inflation to have lasted at least sort of 50 or 60 e-foldings. So observationally, we're only probing a small range. In the future, things like Lyman alpha forest, 21 centimeter, the spin flip of neutral hydrogen, may add a similar range of scales, another 5 to 10 e-folds. But even then, we're still only observing a small fraction of all scales. This, of course, limits our ability to constrain the physics of the early universe, because we are only really sensitive to the amplitude of the perturbations from inflation over quite a small range of scales. So what's wrong with the smaller scales? You know, that we do actually observe, for example, the solar system with incredible accuracy. There are really high precision tests of gravity using solar system physics. The problem is the solar system doesn't have any memory of the initial conditions on the scale of the solar system. The solar system, we purely see late time, relatively late time physics from gravitational collapse, which has got nothing to do with the initial radiation perturbations present in the first sort of second after the Big Bang. So radiation pressure and the chaotic solutions to gravitational collapse really erase small scale memory. And where we observe perturbations today, well, where we observe primordial perturbations today are the scales which remain roughly linear today, so greater than about the megaparsec scale. So once again, this just shows, sorry, it's not very high resolution. Over 3 or so orders of magnitude, we observe the primordial power spectrum to be close to scale invariant and quite simple and boring. But what we need then is for it to grow significantly on smaller scales if one wants to see any primordial black holes. So the idea is something like this. Again, the amplitude 2 times 10 to the minus 9 on CMV scales, but then on some smaller scale, you rise up to a peak and then decrease again. And in total, you want around 50 e-folds, and we are observing less than about 10 e-folds. How large this peak needs to be depends on the details of, well, various things, but it doesn't depend very much. And you need to hit an amplitude around 10 to the minus 2, perhaps 10 to the minus 3, to form any primordial black holes at all. So the example I've been talking about yesterday was ultra-slow roll inflation, where you have some inflection point. Here's an actual example based on reconstructing the potential work with Pipper and Sabot again. And the inflection point here, it's too short to actually see by eye. The flat part is very, very short, but that's enough to produce this boost in the amplitude of the perturbations by 6 or so orders of magnitude. Okay, so although it's very short, because remember the kinetic energy was decreasing like a to the minus 6, it can spend a long time on a very short flat part. And then once you leave the flat part again, it reaches slow roll. And then you can see in this figure, depending on how you re-enter the slow roll attractor, depending on what happens to the shape of the potential after ultra-slow roll ends, sometimes the perturbations stay very large, sometimes they decrease again. And here we're sort of fine-tuning just to see what we could get. Again, there's no real good prediction that I'm aware of from any sort of motivated model of inflation to say what's more likely or not. Now, it doesn't have to be a single field inflation. If it is single field, then it probably has to be ultra slow roll. But one can think about inflation with more than one scalar field. I won't go into any great details, but there's something called hybrid inflation. Some of you, I'm sure, have heard of, which is where you are rolling down in a valley, but then the second field, called the waterfall field, at some point is destabilized. It flips from having a positive mass to having a negative mass. So at that point, you roll down the side. And as you roll down the side when there's this instability, this can create a large amplitude of fluctuations, typically on scales close to the end of inflation. So you can have this tachyonic instability, meaning that tachyon meaning you've got a negative mass squared, you're rolling down the side, and this can lead to large and also potentially non-Gaussian perturbations. So here one's seeing a plot from large scales on the right-hand side towards small scales on the left-hand side. And depending on the details of the waterfall field, you can have a large boost in the primordial power spectrum, but typically only on the very, very small scales, very shortly before inflation ends, because once you've destabilized the inflaton attractor, you typically hit the minimum quite quickly within a few e-foldings, and then inflation ends. So this is a method to generate light primordial black holes, but not one to generate anything like LIGO mass, because those scales are still quite large. They're not very far away from the observable scales, hiding over the right-hand side here. Okay. Another idea is you can have particle production during inflation, depending on the couplings of the inflaton field to any other light field, or perhaps not even light field during inflation. So you can have some boost, some temporary peak, and where this spike occurs can be tuned depending on the models you choose for the Lagrangian of your inflaton. But there is always some degree of tuning. This won't just happen by itself for no reason. You'll need something special to happen in order to create a peak during inflation, a large peak. So generically, we need the power spectrum to grow by about 6 or 7 orders of magnitude. To study such a case, you should not use the normal spectral index and the so-called running of the spectral index, which is the derivative of the spectral index with respect to K. Basically, all of these parameterizations are likely to break down if you go too far. If you go to too strongly scale-dependent cases. Okay, so if the power spectrum turns blue, meaning if it grows to become larger on small scales, so the spectral index is larger than 1, then you would expect the very smallest scales to form the most primordial black holes, which will form the very lightest ones, because the horizon scale at the end of inflation on the smaller scales is small. So to have something other than a relic, or basically evaporated primordial black holes, you need a localized peak, which then decreases again. These are generic arguments. They're not, there may be ways around them with very specific cases, but in general, if the trigger for the boost in the power spectrum comes from the end of inflation, you're only producing very light ones. Now, I want to show you quite soon the constraints on the primordial power spectrum from primordial black holes. But there's not only a constraint from primordial black holes, so I also want to show 2 other constraints. I won't have time to show the calculations in any detail at all. But for those of you who have done a first course in cosmology, you will have been taught that in perturbation theory, the scalar vector and tensor perturbations decouple. And that's what I was assuming on Monday when I was talking about the amplitude of the tensor fluctuations, the power spectrum, and the amplitude of the scalar or curvature perturbations. Okay. However, if the scale of perturbations become very large, then you have to look at the nonlinear coupling, nonlinear interactions, and a large scale of power spectrum will induce gravitational waves. And there'll be some particular mass scale associated with the horizon scale and also some particular frequency. And it turns out that the pulsar timing array can see sort of solar mass, the equivalent horizon mass to a solar mass, LISA much smaller, 10 to the minus 10, roughly the asteroid range. LIGO, it's not very sensitive, but it would see even much lighter, 10 to the minus 18 or so solar masses. And finally, there are spectral distortions, but maybe in view of the time, I'll just say that basically the CMB looks to be a perfect black body, but if there was energy injection from fluctuations in the CMB, then that would look like an additional perturbation, which could cause a deviation from a perfect black body. And we haven't seen that. As far as we know, the cosmic microwave background temperature follows an exact black body spectrum. So put that all together, I'm giving references if you want to see the details. Here on the large scales, again, remember, smaller values of K correspond to physically large scales. So here we have the CMB, we've got large scale structure on scales larger than a megaparsec. And the amplitude of the fluctuations is very small, 10 to the minus 9. Then we have some other constraints from the lack of distortion to a black body. We can have a constraint on the power spectrum of order 10 to the minus 4, but not a detection. From searches for a primordial gravitational waves from the pulsar timing array, this has a constraint on about 1 solar mass horizon, which corresponds to about 1 solar mass primordial black holes. And everywhere else, the only current constraint on the allowed amplitude of the power spectrum comes from the non-detection of primordial black holes. And this line, notice it's quite close to flat. It's around 10 to the minus 2, 10 to the minus 3, closer to 10 to the minus 2. Now, the details don't matter, but the exact amplitude of this constraint depends on the shape of the primordial power spectrum. Okay. So it depends on whether the peak you assume that you've got on this particular scale, whichever scale you're looking at, is either narrow or broad. And there's this interesting coincidence again around the LIGO mass range. It's also where the pulsar timing array is quite constraining to the level that if the power spectrum really was 10 to the minus 2 on these sorts of scales, you would probably expect to see the second order gravitational waves as well. So there may be, a slight tension there, but the calculation uncertainties are large enough to excuse the slight overlap. And that's also where the QCD transition is taking place. So, this is a very interesting mass range to look at the moment with current data. And I'll derive this equation relating where this upper bound on the power spectrum, how this relates to the allowed fraction of primordial black holes, but you can see it's only logarithmically sensitive. And that's why this line looks so flat. So even things which might not exist, such as primordial black holes, can matter, okay? Because, if the power spectrum was too large, they would have formed, and then we would have seen them. So the inference from their non-existence is still an important physical conclusion. I think I'll skip this in view of the time. You can ask questions in the office hour. I briefly want to talk about relics. So just the idea that, so primordial black holes decaying today or decaying in the past, so if they had formed with a light enough mass, then the Hawking radiation can be important. Hawking radiation is inversely proportional to the mass. So for a heavy black hole, an astrophysical mass black hole, the radiation is absolutely negligible. But for those which are light, it's not negligible. And towards the end, the decay becomes very important as the mass goes towards 0. Now, what happens at the very end as the mass really hits 0, nobody knows, because we don't have a theory of quantum gravity. So we don't know if these evaporate to nothing or if they leave a Planckian mass relic. And arguably, in all honesty, because if the rise in the initial amplitude of the perturbations is related to the end of inflation, this should occur on very small scales when the horizon mass is very light. So perhaps the most likely scenario is that they would be in relics. Unfortunately, this is probably impossible to detect because they're very, very light, but they're stable. We won't see them annihilating, and their number density is clearly much larger than a heavier black hole relic, but nonetheless, compared to a particle dark matter model, their number density is absolutely minute because their mass, the Planck mass, is huge compared to any particle dark matter mass. However, there was a paper, I've not really got to grips with it, but I'm just throwing in the reference. You can see the archive number here, claiming that as the black hole evaporates close to nothing, the black hole mass, the relic mass, becomes comparable to the mass of the ejected quanta from the black hole, and that this could give a huge kick to the relic and give it a large thermal velocity of order 10% of the speed of light, which would no longer be called dark matter. So maybe on theoretical grounds, this can be ruled out already. As I say, it's a new paper. I haven't heard any professional reaction to it, but it's a very active field, primordial black holes. There's papers literally every day. There was one this morning on the archive. It's hard to go a day or more than 2 days without a new paper. So there we go. Primordial black holes, they're one of a huge number of dark matter scenarios. And the truth is we have no idea which one is correct. And you've heard about some of these from Laura, but of course there are many more. The reason why I'm interested in primordial black holes, I don't for a second say they're more likely than any of the others, but rather just that they're special because they're not new physics, they're rather new initial conditions. And that I think is interesting. That they're quite unique in that sense. Okay, again, I'll skip this. Just to throw out a random possibility that you may have heard of Planet 9. This is not Pluto, but there's some evidence looking at the rotation of either Uranus or Neptune, I've forgotten, or perhaps both, that there is an additional planet even further away. And I just like the idea, perhaps it was a primordial black hole which became trapped by the gravity of the solar system. And if you print out the paper in A4 size, they've got an exact one-to-one illustration of a 5 solar mass primordial black hole. Okay, so we see against the width of the paper. So that's how tiny it would have to shrink. If you think for the Earth, it would have to shrink to something like the size of, well, maybe not much more than your thumb. But, it's quite a, let's say, original scenario. Let me now just go on to, well, what would happen if there was a definitive detection of one primordial black hole? Well, then we would know what some of the dark matter is, because any primordial black holes will be some dark matter. It would be the oldest relic detected, predating the Big Bang nucleosynthesis by many, many orders of magnitude, closer towards the Big Bang. There are lots of other potential relics, primordial gravitational waves, defects, cosmic strings, spectral distortions, ultra-compact mini-halos. There are many things people are looking for. Unfortunately, none of them have been found. So basically, we see evidence of Big Bang nucleosynthesis, we see indirect evidence of inflation, but no evidence of what happened in between those two epochs. Even though in terms of the growth of the scale factor, it's actually a long and important period in between. One thing I can tell you, and this is the only non-trivial thing I'll say about mixed dark matter models, is that if some of the dark matter is in primordial black holes and they're not terribly light, so they're more than 1/1,000,000th of the mass of the sun, then their huge mass will create a strong gravitational attraction at the time of formation, and they will form a cloud of dark matter, the rest of the dark matter particles around them. And if the rest of the dark matter was a standard WIMP, then the WIMPs would be able to annihilate. And because the annihilation rate is proportional to the density squared, the very large density around a primordial black hole would create a very bright signature of gamma rays from the annihilation of WIMPs. And that's because of this very steep density profile with a very high density core, which can only form in the early universe. You'll never get such a steep and dense density profile forming at late times after sort of stars are formed. So this would be a smoking gun, and really, I think the honest conclusion is, if WIMPs are detected, then we know there are no heavy primordial black holes, and vice versa. If LIGO really did detect a sub-Chandrasekhar mass primordial black hole, then we know that can't be all of the dark matter, but we also know the rest cannot be WIMPs. Yeah. Okay, so, well, looking forwards, one thing to keep your eye out is for the pulsar timing array and nanograph calibration, especially, which have found some tentative hint of a signal, most likely astrophysical gravitational wave signal, but nonetheless, there's always the hope it could be primordial, which is very closely related then to LIGO mass scales. In the further future, LISA and other ground-based detectors will be much more sensitive to gravitational waves over a much larger range of scales. We'll have better probes of the spins, of the mass ratio, etc. Personally, what I'd really like is the detection of sub-Chandrasekhar mass object. Okay, so here again is a plot involving work by Pippa and others. In fact, other PhD students of mine, or former students. Okay, so something like a Pixie experiment could measure mu distortions down to about the level of 10 to the minus 9, perhaps even a guaranteed detection if they could reach a factor of a few tighter. Then the square kilometer array will look for pulsar timing as well. There's LISA, Einstein telescope, etc. So, and this line now corresponds to 0 primordial black holes inside the entire observable universe. Okay, so, the future actually looks quite bright in the next few decades. And in the short time scale, I think the most interesting is really the LIGO mass. But who knows? Good new ideas, like the idea that a primordial black hole relic will be moving too quickly to be cold dark matter, means that maybe theorists can get there first and rule out some ranges without new data, just by having new ideas. Okay, hopefully I haven't been too fast. I've reached the end with 5 minutes to go, so let me summarize. It's still possible for all of the dark matter to be in the form of primordial black holes, at least within the sort of asteroid mass range, so around 10 to the minus 12, 10 to the minus 15 solar masses. There have been various attempts to rule out that mass range. None have stood up to scrutiny. All the other mass ranges are, let's say, controversial. But mixed dark matter models are also interesting. Some combinations, such as primordial black holes plus WIMPs, are ruled out. It's still possible that some of the LIGO-Virgo black holes were primordial, but not all of them. And whether or not primordial black holes exist, the search has taught us about early universe and inflation. It's taught us important things. So let me finish with a quote from the same Quantum magazine article I gave earlier. So going back to my hope, so finding just one black hole mass of subsolar mass, which should be common according to the primordial black hole scenario that's based on the QCD physics, and which can't form from stars, would transform this entire debate. And I'll